For all of human history, curious men and women have looked to the heavens above. They saw stars, the moon, and comets, but also constellations, gods, and omens. It sparked fear and wonder, and for a long time remained a mystery. Cave paintings made over 16 millennia ago were found in France. They depict wildlife like horses and bulls, but some elements bear striking resemblance to the night sky. Groups of stars we today call the Orion Belt and the Hyades Cluster. Early astronomers like Aristotle observed the stars from different latitudes. They realized that the Earth was round, a sphere they believed to be in the center of the universe. It took over 1,000 years until Copernicus understood it wasn't. The Sun, not the Earth, lies in the center of the solar system, Earth and other planets orbiting around it. The invention of telescopes allowed a closer study of our neighbors. New planets and moons invisible to the naked eye were discovered. Soon, many imagined worlds not unlike Earth. Mars was thought not only to be habitable, but also inhabited. Observations by Schiaparelli were misinterpreted and sparked belief in an alien race carving canals across the red planet. Today we know humans are the only intelligent life in our solar system. And while planetoids like Jupiter's icy moon Europa might meet requirements for very basic life, we must look farther to find potentially habitable planets, or even a second Earth. There are over 100 billion stars in our galaxy, many in the center of their own planetary system. Distant planets, light years from Earth. They are called exoplanets, and this is how today's astronomers look for them. Traditional astronomy is carried out by ground-based telescopes. For over 50 years, the Arecibo telescope in Puerto Rico was the world's largest single-aperture radio telescope. In 1990, astronomer Alexander Boltzmann, using the Arecibo telescope, discovered a pulsar. Pulsars are fast-spinning stars that emit beams of electromagnetic radiation along their magnetic poles. Like celestial lighthouses, a pulse of radiation can be seen with each rotation. Pulsars spin extremely fast, up to 1,000 times per second, and their pulses have a very regular frequency. This pulsar, B1257+12, was different. Surprisingly, its pulses were not regular. Boltzmann observed changes in their frequency over time. Those changes could only be explained by the presence of several large bodies. As they orbit around B1257, their gravity pulls on the star, slightly altering its rotation. The first ever exoplanets had been found. They were named Draugr, Poltergeist, and Phobetor. Boltzmann's method, today called the timing method, only works for pulsars, not for regular stars like our Sun. Those so-called main sequence stars are far more numerous throughout the galaxy. Astronomers would soon devise and refine many more detection methods. The search had begun.
The most successful way to discover an exoplanet is to observe it while it is passing in front of a star. This is called eclipse or transit. During a transit, the relative luminosity of the star is reduced because the planet blocks a part of the light. In order to find new exoplanets, we continuously measure the brightness of a star over a long period of time. Now, the measured light intensity is plotted against time. Astronomers call this a light curve. When we observe 3 consequent reductions of brightness with the same period of time, their cause is considered to be an exoplanet. In order to discover new exoplanets, the same part of the sky has to be monitored continuously. This is why Earth-based observations are difficult. Earth's day and night cycle prevents a continuous observation with just one telescope. However, using this method, we can only find exoplanets whose orbit plane is parallel to the line of sight to Earth. For all other exoplanets, we must employ other techniques, but more of that later. Using the transit method, we can also find out about the contents of an exoplanet's atmosphere. During a transit, a small part of the star's light shines through the exoplanet's atmosphere, causing absorption lines to appear in the spectrum. The spectrum is measured by observing the transit at different wavelengths. These absorption lines can be assigned to different chemicals. This is how we can identify gases in the atmospheres of exoplanets. And this is how we know that Kepler 1b's atmosphere, for example, consists of nitrogen and carbon dioxide. Of special interest are the absorption lines in the infrared spectrum. Many elements absorb in the infrared, like for example water. So if we want to find water on other planets, we have to observe them with infrared cameras. Unfortunately, Earth's atmosphere also absorbs the infrared light emitted by an exoplanet. These are the reasons why we need spaceborne telescopes for our search for Earth-like exoplanets.
One of these is the Kepler Space Telescope. Its mission is to detect exoplanets, and to this date it is the most successful, with more than 2,300 discoveries so far.
It has been launched in 2009 from Cape Canaveral and is sent on an orbit around the Sun, continuously monitoring a portion of the sky. With its fixed field of view of roughly 10 by 10 degrees, transits of planets with long orbit periods can be discovered. Its search for exoplanets began in May 2009. By the end of 2011, the telescope discovered more than 2,300 exoplanet candidates. But these are not confirmed detections. Ground-based follow-up observations are often necessary.
But in July 2012, a tragedy was on the horizon.
The first reaction wheel, responsible for the spacecraft's orientation and critical to the mission, failed. But gladly, the engineers built in a redundancy for that case. For rotating the spacecraft in 3 dimensions, 3 reaction wheels are necessary. The spacecraft has a redundant 4th reaction wheel. They are put in a special configuration. Any of them can fail, and the spacecraft remains fully maneuverable. This configuration is called a pyramid configuration, because each reaction wheel sits on the side of a pyramid. Unfortunately, in May 2013, a 2nd reaction wheel failed.
Unfortunately, it means the spacecraft can no longer focus on its initial target area.
The scientific goal could no longer be fulfilled.
During the next months, ideas were collected on how to put the telescope to good use.
Then in late 2013, the K2 mission has been announced and began operation in 2014. The solution for the 2 missing reaction wheels is to make use of the thrusters.
However, the solar radiation pressure is strong enough to drain the fuel of the spacecraft quickly if it has to constantly act against it. This is why the spacecraft is oriented in such a way that the solar radiation pressure generates no torque. One could say it's balancing on the sunlight.
Now it observes different fields in the sky, depending on where it is currently facing. Each field is being observed for 83 days. So the Kepler Space Telescope was able to operate until it ran out of fuel in 2018.
Kepler was the most successful telescope when it comes to the number of detected exoplanets.
But Kepler's successors are catching up. The space telescope TESS has been launched in 2018 and uses its 4 cameras for the search for exoplanets using the transit method. While there are only 147 confirmed exoplanets discovered by TESS so far, more than 4,000 exoplanet candidates already have been detected by the telescope. One of the most challenging methods for detecting exoplanets is to directly take images of them. This is extremely difficult because in the visible part of the spectrum, the host star is a lot brighter than the exoplanet. This is why astronomers choose infrared telescopes for direct imaging. The planet's thermal emissions have a higher intensity than the light reflected by them in the visual spectrum. In addition, the host star's light has to be blocked with a coronagraph, which is blocking the light from the star. Now the exoplanet becomes visible. Here we see an actual image of 4 exoplanets taken from the Keck Observatory in Hawaii. Looking at our solar system, we find that it has 8 planets. So the question arises, if other stars could also have more than one planet. And yes, it turns out that there are systems like Kepler 90 or TRAPPIST-1 with multiple planets. Let us take a closer look at the TRAPPIST-1 system, only 40 light years away from Earth, so basically just around the corner.
The star TRAPPIST-1 is only slightly larger than Jupiter and only has a surface temperature of 2500 Kelvin, which is not very much for a star.
This is why astronomers classify it as an ultra-cool dwarf. But how do we know that the system has so many planets?
The light curve will be different for transits of planets with different sizes and different orbits.
The transits vary in period, length and intensity. Here we see the transit light curves from all known planets of TRAPPIST-1. These are actual measurements taken by the Spitzer Space Telescope. One can clearly see that the transits take longer and have a lower relative luminosity the further away the planet is from the host star. By the way, let me briefly explain the naming convention for exoplanets. Typically, the host star is named after the discovering telescope, plus a number for categorization. So the TRAPPIST-1 system has been discovered by the TRAPPIST telescope, located at the European Southern Observatory. Then, each planet is assigned a letter. The letters indicate the order of discovery, not the order of the planets in the system. It is just coincidence that both match in the case of TRAPPIST-1. There is also a more sophisticated method of detecting multiple planets in a system. It is called transit timing variation. Using this method, a second planet in the system is not directly observed, but discovered by variations of timing in the first exoplanet transits. The gravitational forces not only act between the planets and the star, the planets also attract each other. In certain constellations, this can speed up or slow down the frequency at which transits occur. A transit might be observed earlier or later than expected. So if we find variations of the transit timings, there must be another planet in the system. By measuring these variations, we can also determine the mass of the second planet. This is how the masses of the planets in the TRAPPIST-1 system have been determined.
In 2013, the European Space Agency launched Gaia aboard a Soyuz rocket. The spacecraft's mission is to observe and catalog 1 billion stars of the Milky Way. Gaia was placed at the L2 Lagrange point, where it orbits the Sun alongside Earth. With the help of its sunshield, its view of the stars is uninterrupted by sunlight. Over the course of 1 year, a complete map of the celestial sphere is constructed. The following repeat observations allow a precise measurement of each star's motion through our galaxy. Through this data, astronomers will get insight into the formation of the Milky Way. but the motion of the stars can also reveal exoplanets. This method is called astrometry. When a planet orbits a star, not only does the star's gravity pull on the planet also pulls on the star. The closer and more massive the planet, the greater the effect on its parent. Both bodies rotate around their so-called barycenter. The star appears to wobble in the sky. Astronomers monitor the angular distances between neighboring stars. If these distances change, they might have found a wobbling star. The chances are high it would also have one or more exoplanets. While to date only very few exoplanets have been found by astrometry, up to 50,000 new discoveries might be possible through Gaia's star catalog. Astrometry only works when the orbit of an exoplanet is relatively perpendicular to the observer. The orientation of any exoplanet's orbital plane, however, is random. When a planet's orbit is almost aligned to our line of sight, but not enough to cause a transit, the radial velocity method can be used. Like before, this method relies on the wobble of a star caused by the gravity of one or more exoplanets. As the planet orbits around its star, the star alternates between moving towards and away from the observer. Like the sound of a police car siren changes while driving past you, the starlight's wavelength changes depending on the star's movement. This is called the Doppler shift. When the star moves away from the observer, the light waves are stretched out, resulting in a redshift of the starlight's wavelength. As the star changes its direction towards Earth, its light waves are compressed, the wavelength gets shorter and shifted towards blue. The radial velocity method is one of the most successful ways to detect exoplanets. It is often used to confirm discoveries by other methods. Einstein's theory of relativity redefined our understanding of gravity. Massive objects like stars and planets warp the fabric of space. Light is also redirected by these gravity wells. Images from behind the star become distorted. As the lensing star travels in front of other stars, their light gets focused onto the observer and their brightness increases. This is called gravitational microlensing, and it turned out to be yet another tool for astronomers to look for exoplanets. This is what a lensing event looks like. Watch the orange star as the lensing star approaches from the left, as well as its brightness as seen from Earth. As the lens gets closer, a second image of the orange star appears to the left of the lens. The brightness increases until the orange star is right behind the lensing star. At the height of the event, the orange light is bent all around the lensing star. Then the brightness decreases again until the right image of the orange star disappears. What happens if the lensing star has an exoplanet? Now, not only the star itself becomes a lens, the planet also causes a small lensing effect. The brightness increases as before and reaches its maximum when the orange star is right behind the lensing star. Shortly after, however, the exoplanet moves in front of the orange star. A short spike appears in the brightness diagram, revealing the planet's existence.
To this day, more than 4,400 exoplanets have been discovered. The vast majority of them with the transit method, but the radial velocity method ranks second, with 20% of all exoplanet discoveries. We now know of the existence of other worlds, some even in the habitable zones around their stars. Future missions, like the James Webb Space Telescope, will reveal the existence of even more exoplanets.
And although the interstellar distances are far too large to travel there, we might one day detect intelligent life on a planet far away. Another blue planet that might be somewhere out there. This is the reason why we will keep looking.